Now, as Greg mentioned, my name is Eric, and I'm a PhD student at the Australian Maritime College, and I'm researching the effect that moorings or the effect that mooring systems have on floating wave energy converters. Now, generating renewable energy from ocean waves is an interesting idea in theory, but in reality, it's particularly challenging. This is largely due to the irregular nature of ocean waves and the immense energy stored in those waves during an extreme sea state, like a tropical cyclone or a deep low pressure system. Now, from a commercial perspective, it is very difficult to design a device that can constantly produce electricity given the wide range of operating conditions, while mitigating the risks with those extreme waves. And in the short term, it appears that wave energy is not going to supply an enormous amount of energy to the world's electrical grids. However, there is a very useful application for this technology, which involves integrating it into offshore systems that currently generate their electricity requirements with diesel electric generators. In this application, wave energy converters not only supplement the energy requirement, but can also dampen the environmental forces to help protect assets or structures in the wave field. A good example of this is the emerging offshore aquaculture industry that we're seeing at the moment. Now, from a historical perspective, many wave energy converters have been designed for the nearshore region, and this is largely due to the technical challenges of bringing the energy from the actual converter or the array of converters and back to the shore where the electrical market is, or the grid. Now, there is interest in moving wave energy converters from the nearshore region into more open waters, and this is to try and take advantage of the additional energy that's in deep water waves. Now, inevitably, as wave energy converters move further offshore, they're going to need to float, and once they start to float, we're going to find that the mooring system is a very important component of a floating wave energy converter. Now, the moorings perform two main functions in this application. The first is, obviously, for station keeping. We want to make sure that the device is going to survive the extreme sea states. However, we also want to make sure that the motions of the device are happy in those operating conditions. Now, what I thought we might do is just start with some of the generic wave energy converter archetypes that are around. Now, there are lots of variations on these particular types of devices. Some of them overlap, but in general, these are the four main ones that I think of. So the first type is called an oscillating water column. Now, an oscillating water column is a big hollow structure that has an opening at the front of the device, and it's open to the sea. And as the waves interact with the device, the water on the inside of the chamber oscillates up and down, and this displaces the air that's in the chamber over a turbine foil, which in turn creates electrical energy. So we're converting pneumatic energy into electrical energy. Then we have a wave-activated body, which is a device that's designed to become excited by the actual incoming waves. And the excitation of these waves generates very large structural motions, and the kinetic energy from those structural motions is then converted into electrical energy. Then we have devices which are called overtopping devices, and these basically are reservoirs that contain water that is above the mean surface level of the water. And so when the waves interact with an overtopping device, water runs up into the reservoir, and the gravitational potential energy of the water then runs back through a turbine, producing power. Finally, we have pressure differential devices. Now, the pressure differential devices are big rubber membranes that sit on the seafloor, and as the waves pass over the top of the device, the hydrostatic pressure fluctuates, and the fluctuation of this pressure is then converted into electrical energy. Now, there are lots of devices that overlap in this application. So there's a type of wave energy converter called a spar buoy, which is a wave-activated hull. The hull's designed to resonate in Heave, but the power takeoff system is an oscillating water column. And there are lots of different types of these devices. So if I step back a tiny bit, here we have an example of an oscillating water column. This is the the wave swell King Island device that was deployed earlier this year. And then we have a wave-activated device, which is a big pendulum. This was tested by a company called AMOG. And so there are lots of different permeations of how these wave energy converters work. Now, sorry. So the device that I'm working with is the Oscillating Water Column. It's a very simple concept. Okay, there are no moving parts below the surface of the water. The operating principles are mechanical systems that we understand relatively well. For example, the water that oscillates up and down on the inside of the chamber is kind of like the way a piston behaves on the inside of an internal combustion engine. And the power takeoff system uses an aerodynamic turbine, which again, we have quite a lot of experience collectively on how these sort of turbines will work. Now, of course, there is a fair bit of learning to be taken because unlike a lot of other turbines, the oscillating water columns, they fluctuate relatively quickly with what the wave periods are doing. So you have different directions for how the turbines will interact with the flow of the air through the chamber. Now, there's lots of academic research available for loads of different wave energy converters, including OWCs. But unfortunately, there are very few full-scale devices out there in the real world. And this makes it difficult to understand what the real-world performance is actually like for these devices. And when it comes to designing like a new device or for developing technology, performing a similar vessel analysis becomes challenging. So what I wanted to do was step through the design process that I used quickly to design the device that I'm actually testing in my current studies. Now, it's a multi-stage process. The first thing that you need to do is you need to design a high-performing chamber. Now, this is an asymmetrical chamber, being that the forward lip is relatively close to the water plane, and the side and aft walls of the chamber are relatively deep. Okay, so this is one type of many different types of OWCs. Once you've designed a high-performing chamber, then you need to design the external geometry that will help the chamber float, and those will govern what the motions do. And then lastly, you need to design your moorings and your power takeoff system and all the other equipment that you need. Now, it's important to note that there are no design standards for wave energy converters at this stage, which means that there's quite a lot of uncertainty in how these designs actually work. And so I have some pretty major questions that I'm investigating. The first one is how does motion affect the hydrodynamic performance of these devices? Is motion a good thing? Is it a bad thing? What types of motion do we want to encourage, and what kind of motions do we want to repel? Now, when it comes to motion and wave energy converters, it depends on the type of device that you're building. If you're trying to make a wave-activated body, then motions are good because you can generate a lot of kinetic energy and convert that to electrical energy. But for some wave energy converters, motion is bad because that motion dissipates the total amount of energy that's available, and that reduces the overall performance of the device. And then when you start to think about floating structures, you're going to have coupling between different degrees of freedom. So you're going to have heave and pitch and surge and a whole lot of different degrees moving at any one time, and how those interactions affect the performance is difficult to know. So once we understand the effect of motion, we want to know what mooring configurations will promote beneficial motions and suppress those undesirable ones so that we can, find a balance between improving performance yet surviving extreme sea states. Now, to design one of these OWC chambers, there is heaps of really good information. Now, there's a gentleman, Ahmet El-Nafi, did quite a lot of work in his PhD on oscillating water columns before me. And a lot of the work that he's done has focused very heavily on the performance of these chambers. Now, the process that I went through basically was to identify the peak wave period and the significant wave heights for the operational conditions and the survivable conditions at a general location where this device might actually go. Now, the device is not being built for a specific location, so the significant wave height and peak periods are typical for the east coast of Australia. Now, the chamber length of the device is relative, or the optimal chamber length is relative to the incoming wavelength. So what you do is you work out what your wave period is, you work out what the respective wavelength is, and then the chamber length should be about 12% of what the actual wavelength is. Once you've got that main parameter sorted out, then you need to start adjusting the forward lip and the depth of the side lips and the width of the chamber so that you can match the natural period of the water that moves inside the chamber with the peak wave period. This way, you've got a chamber that's designed to absorb maximum energy where the maximum energy is actually available. Now, it's important to note that the forward draft of the wall at the front and the side and aft wall drafts or depths are critical parameters for these devices. If you decrease the forward draft and increase the side draft and aft draft, you will increase the performance. However, if you decrease the forward too low or too little, then what will happen is you will breach air from the chamber, which will be bad for your performance and probably very bad for all the turbine machinery, your power takeoff system. Now, when it comes to predicting the performance, this is a very good bit of research that was conducted, and it's essentially an empirical model which you can take a bunch of equations, put it into some sort of a programming language where you can change the different geometrical parameters, and it will give you a prediction about what the performance does. Now, I used this and then I validated the performance with a CFD, or a computational fluid dynamics simulation, and it worked it was quite accurate. So this is not a bad way of looking at things. Now, some people are starting to look at the effect that external geometry has on the performance of these devices. And in this little bit of work, somebody's looking, there we go. The author of this work has been looking at how these Harbour walls increase performance. And what they essentially do is they take wave energy from a wider region and concentrate it along the forward wall of the OWC chamber, which is great because in the operational condition, you can make more power. But in the survivable condition, you're going to concentrate an enormous amount of energy onto that front wall, which may be detrimental. Depends on how the design of the structure actually copes. Now, a little bit further with the external geometry, some of the design unknowns. There are no design standards at this stage. Nothing from DNVGL, nothing for API. And that leaves a lot of questions like, what are the natural periods that we actually want to design these devices to? How stable does the structure really need to be? Normally they're unmanned. So, we don't want the thing to capsize, but motion is likely to happen. Do we need reserve buoyancy? What sort of topside payloads do we need? Now, remembering the motion is a really important part. Do we want motion or do we not? It depends on how the structure actually performs. Now, the general arrangement of the device that I'm testing is pictured here in the left-hand side picture. It is a column-stabilised structure similar to a semi-submersible platform. All of the buoyancy, or most of the buoyancy, comes from the columns that are around the outside of the device. We have large Harbour walls to concentrate extra energy into it, and we have an enormous heave plate around the outside and around the back of it. Now, the function of the heave plate is to try and remove or separate the structural motions of the device so that there is a large range between the water that's oscillating on the inside of the chamber. We're trying not to get the structural motions to interact with the fluid motions inside the chamber. Now, this device has been designed so it has a GM greater than 5 metres. It can accommodate a 45-tonne topside mass. The forward wall has a draft of 2.7 metres, and it's symmetrical along that plane. Now, the experiment that I set up was based around understanding what we actually want from our mooring systems. Now, to begin with, I set up 3 different conditions. The first was a fixed condition where there is no motion from the device whatsoever. So this is a layout of the model test basin at the Australian Maritime College, and we have our OWC here in the middle. And in the fixed condition, the device was sitting on top of a small table that doesn't have too much effect on the wave field. And then it was ballasted down with about 60 kilos of weight so that it was really secure. And It was tested in 39 millimeter, 50 and 60 millimeter regular waves across a very wide across a wide range of different wave periods. What this fixed condition did was gave me a very good baseline about one, how it performs, but also how the fluid interacts with the the chamber and how the power takeoff system may actually work. So it's a good baseline. Then I set up a second mooring configuration, which was designed to allow the device to heave and allow it to pitch, but to constrain surge as much as possible. Now, to do this, the device was free floating, and I stuck two different moorings onto the fair leads, which were located at the center of gravity of the device on the side of the column chambers. And the mooring lines were run forward horizontally at 45 degrees and afterwards. And so this really constrained those surging motions, but it didn't really restrict the heave or the pitch too much. Now, the second mooring condition that I tested was designed to allow the device to heave backwards, to surge, and to pitch at the same time. And the way this was achieved was with a typical horizontal soft mooring. So the mooring line came off the fair lead as per the other condition. There was a spring inside the mooring line, which allowed the device to be able to surge backwards, but also to restore. And then it was fastened off onto the side of the model test basin. Now, aside from the experimental fluid dynamics, I'm also looking at I am using computational fluid dynamics. Now, the data that's collected from the experiment is used to validate the experimental or the computational fluid dynamics simulations, because there's a lot of the CFD can be difficult to get good outcomes from if you haven't got the parameters set right. Now, the CFD simulation is composed of two different types of meshes. We have a background mesh, which contains the boundary conditions for the simulation. It contains a region for the atmosphere, a region for all the fluid. It has the free surface interaction, or the free surface area where the waves are. And then what we have is an overset region which surrounds the geometry of the model. And what the overset region does, in essence, is it calculates what the fluid pressure is around the outside of the model at each time step, and then updates what the motions are. And it allows the overset mesh to interact with the background mesh, so that we can essentially model what the motions are of this device and how the air inside the chamber and the waves interact with the outside of it. Now, the software that I use is Star CCM, and the simulation it's only half of the actual model. Because the device is symmetrical, we can save a lot of that computational requirement by only simulating half of it. Rightio. Now, what I have is a couple of different photographs of the experiment, or the first experiment that I did. Now, what I want to point out is these balls that are sitting on top of the device. Now, this is how we measure the motion for a floating structure like this. So what happens is we've got around the outside of the model test basin a series of different cameras that are looking at the location of each of these balls. And because there are 8 cameras in various positions, the software can basically triangulate how the relative position for each of those balls has changed, and then it can compute what the heaving motions are and the pitching motions without actually having to interact with the model itself, which is good. Now, down here on the bottom left, I have the little table that was used to constrain the device. It's very minimal. It's unlikely to have had a huge effect. In fact, the computational fluid dynamics simulations suggest that there may be 1 to maybe 3% effect from the table on the performance of the device. Now, on the bottom right-hand side, we have this is how I'm simulating the power takeoff system for the device. Now, there is no actual turbine and generator on it. The device is a 1 to 36 scale, which makes it too small for that to be realistic. So what we do is we simulate the turbine or the power takeoff by creating the same amount of resistance that we would expect the power takeoff system to actually have. So when the water oscillates inside the chamber, what we have is the turbine is going to create a certain amount of resistance, and that's going to affect and slow down the volumetric flow rate of the air that passes through and increase the pressure. And one of the big challenges of the design side of this is identifying what is the right amount of turbine damping that we actually need, and how do we model that so that we have something realistic in the real world. Now, as a rule of thumb, the size that orifice needs to be should be somewhere around 1/2 to about 2% of the water plane area of the actual chamber. That's a generalization, but it's relative to the type of device, how the device moves, whether the device is fixed, and what sort of turbine that you'd like to have. Now, the turbine that we're simulating in this case is a bidirectional turbine, which is different to the type of turbine that the wave swirl device is using, which is out there in King Island. That's a unidirectional turbine. Now, because we're looking at motions and the fluid motions on the inside of the chamber, performing decay tests is really quite important. Now, what the decay test is going to tell us is what the resonant frequency is that's exciting the chamber and the actual motions of the device. Now, to perform an experimental decay test on the Moonpool, what I did was I got a vacuum cleaner and made an extension hose and sat very, very carefully on a little table without disrupting the wave field. And I was able to use the vacuum to draw the water level up to a specific depth inside the chamber. And once the vacuum was removed, the water level then decays back to equilibrium, which is what we can see over here on the side, on the left-hand side. Now, if you take the data that you've collected and then you perform spectral analysis, what you're going to find with the Moonpool is that you have two dominant peaks. Now, the first big peak that you collect is going to be something called the piston mode. And the piston mode is the main body of water that's oscillating up and down. It's the piston mode that we're collecting the energy from. So the peak period that this occurs at, in this case, was about 1.3 seconds, is about the area that we're expecting to find peak performance for the device. Thereabouts. It's not exactly, but it's relatively close. Now, the second little peak that we can see down the bottom here, this is called the sloshing mode. And the sloshing mode is when we have a wave that's sloshing forwards and backwards between the forward and the aft wall. So as the water starts running out of the front lip, you end up with a piston mode and this sloshing mode forwards and backwards. And you can actually see the sloshing mode occurring mostly towards the front of the wall and the back of the wall throughout the decay test. Now, I then moved on to in the experiment doing rigid body decay tests, because the heaving motion and the pitching motion and the surging motions are quite important, but especially the heave and the pitch. And what I've got here is a validated CFD simulation to show how this device moves, because it behaves a little unusually. So the simulation was constrained so that the model can't yaw, it can't move and roll, it can only move in heave and pitch. And the only excitation force was the heaving motion in the very first place. And really clearly, you can see that the first motion that you actually get out of it is a pitching motion. It heaves down, it pitches backwards, pitches forwards, it rolls down and forwards and backwards and up and down. And this suggests that there's coupling that's happening between the heave and the pitch motions. Now, when we actually have a look at the heave decay test, what I've done here is so this is only the heave decay test, and in the top left-hand side, we have the heaving component of the motion, and down the bottom, we have the pitch component of the heave decay test. And we can clearly see there's this non-linear response in both of those motions. And when we do our spectral analysis, what we find is there are two peaks corresponding to those different oscillations that are in the decay test. And this is both for the heave and the pitch. There's a dominant peak at around 4 seconds, which equates to 28 seconds, I think, in full scale. And then we have a second peak, which is at around 2.4 seconds. And I think that's somewhere around 15 seconds in the actual wave spectrum. So then if we move across to the pitch decay tests, this was a pure pitch decay test. There was no excitation at all in the heave. And the heaving components of the pitch decay test look remarkably similar to the heave decay test. Same thing down here with our pitching motions. And what we end up with is two peaks that occur at about the same point, although they're inverse to each other. The heave decay test has a dominant peak at 4 seconds and a minor peak at 2.4, but the pitch is opposite. At 2.4, you have a dominant peak and you have a minor peak. Now, if I align those two decay tests so they lay over the top of each other, they're completely independent tests. And the heave decay test had 3 repeats in it and the pitch decay test had 2 repeats in it. And they match almost perfectly. The spectral responses are slightly different, but the wave period is pretty much right on top of where we want it to do. Well, not where we want it to go. They're right over the top of each other. And so what this looks to me like is that this device does not have a heaving motion and an independent pitching motion. Both the heave and the pitch is the same motion. And it's largely to do with the fact that the device has this big heave plate around the outside, but the front chamber is wide open, offering no resistance. So, of course, as the device moves down, you're going to have more resistance on this side rather than this side, which is going to create that the pitching motion. Now, what we've got is here's a video of the experiment when the device was completely fixed. So you can see there's a few ballast weights on the top of it. And this is going to show you the effect of the Harbour walls. So the waves that are coming in are 50 millimeters in wave height, just 50 mils. And the oscillation of the wave concentrating up to the front of the device increases and increases and increases to, you know, somewhere around, I don't know, maybe 150 mils in this case. So what the Harbour walls, what they do, what the effect of it is when that water at this instantaneous moment is up high like this, there's increased hydrostatic pressure, which is forcing extra energy into the chamber. And this has a very big effect on the pressure that's inside the chamber and the flow rate of the fluid as it moves through the orifice. And it has a large impact on the performance of the device. Now, if we have a look at the way the fluid interacts with the chamber and with the device, we end up with a bit of a plot that looks like this. Now, on the left-hand side of our x-axis, what we have are low frequency waves or long wave periods. And then over here on the right-hand side, we have higher frequency waves. And the blue line is the fluid motions on the inside of the chamber as it oscillates up and down. The black line is the magnitude of the water as it runs up the front face of the device. And the red line is the air pressure inside the chamber. Now, if we have a look at the water flow, the water moving on the inside of the chamber, what we see is we have a peak motion that corresponds to the natural frequency as per the decay test that we did. And we can also see that as the wave frequency increases, the magnitude of that run-up increases and increases to the point where we're approaching a factor of 3. So if you put in, you know, a 50 millimeter wave, you're approaching, I don't know, 150 mils for that wave as it runs up the front. We also see that the peak air pressure across those different wave frequencies is actually a little bit higher than what the natural frequency and what the peak pressure inside the OWC chamber is. Now, it seems to me that the run-up has an impact on what this pressure is actually doing. But it requires a little bit more research to really understand this interaction because it's rather complex. Now, let's have a look at the turbine damping coefficient. This is quite important for the power takeoff. Now, the turbine damping coefficients are basically the amount of resistance that the turbine and the power takeoff system will have on the fluid on the inside of the OWC chamber. Now, there are 2 cycles that are of importance. We're going to have a cycle where the water pressure or the fluid motions on the inside of the chamber are increasing, And this is pushing the air out of the chamber, or basically the chamber is exhaling. And then when the water level falls, there is air being drawn into the chamber, and we have an inhale cycle. And for most of the operational conditions, what we have is pretty good agreement between the inhale and the exhale cycle at somewhere around a turbine damping coefficient of 500, thereabouts. However, at this high frequency position, for one reason or another, there is a very large separation between the inflow turbine damping coefficient and the outflow. And this could have, a whole lot of different problems for the actual turbine design, because, if you are designing a turbine to operate in these conditions, and then you end up with this very large variation in the middle of it, you may very well not absorb a whole lot of energy because the turbine isn't designed to work with that range of conditions. Now, in saying that, we may not even see this happen in the real world because we're experimentally testing with regular waves, and with irregular waves, you may not actually see this interaction. But I thought we'd have a look at it anyway. So this plot here is showing what the absolute pressure on the inside of the OWC chamber is doing relative to what the volumetric flow rate of the air as it transmits in and out of the orifice. And this nice, smooth, clean plot is symbolic of all of these conditions. Okay, it's actually this condition right here. We have a nice, clean pattern. Now, if we look at the pressure and flow rate relationship for this condition, what we see is a much more erratic relationship where we have a flow that's in one direction for the inhale, and then we have this crossing over pattern for the exhale. It's difficult to know why that's actually happening at that frequency and nowhere else, but we'll have to see what happens with it as we continue to research. Now, if we look at the motion responses for the device when it was actually being tested, these are the RAOs, response amplitude operators, and the blue line is the surging response when the device was restrained in surge. So obviously, those responses are really quite small. We've constrained the device, so if we have a 50 millimeter wave, it's only moving back, at most maybe 10 millimeters. Okay, so it's really quite constrained. And then if we look at when the device is able to move backwards, so this is the horizontal soft mooring with the spring, the device finds a nice sort of steady state, and then it begins to creep backwards further and further and further and further, just like we would expect most mooring systems to respond with. Now, if we look at the heave motions, what we have going on is, again, the red line is when surge is not constrained. So we've got surge, heave, and pitch happening, and this is the heave response. And if we constrain the surging motions completely, we actually amplify the heaving motions. So by taking away 1 degree of freedom, the energy that's available has been converted into increased heaving motions. And the same thing for the pitch motions. If we constrain surge, we increase the pitching motions. And then when we think back to, well, how does this affect the performance of the device? Because we don't know if the larger motions are good to convert the kinetic energy into electrical energy, or whether we're going to dissipate the energy. Perhaps these larger motions are parasitic, difficult to tell. Now, if we have a look at the actual capture width ratio, this is the hydrodynamic performance of the device. So the capture width ratio is saying if we have X amount of energy in a wave condition and we've absorbed X amount of energy, what's the ratio between what's available and what we've absorbed? And in the fixed condition, when the device can't move, what we can see is at the peak condition, you can absorb approximately 1.5 times the amount of energy that's actually in the wave. Now, this is not the reason why we can absorb more energy in the wave is because we're concentrating additional energy from those harbour walls. If we made the harbour walls even wider, the device would probably absorb even more power. But either way, to be able to absorb 150% of the energy that's a good baseline to work with. Now, if we restrain the surging motions so that it can heave and it can pitch, but not surge or minimal surge, we basically lose about half or a little bit less than half of the energy that we could have absorbed when it was fixed. And we've got this big flat line condition of about 80 to 85% across a really quite a wide range of operating conditions. Now, this is still a very good performing situation to be in. To be able to absorb 80% of the energy that's available, I don't think that's too much of a problem. Now, if we allow surging motions, the performance of the device drops out immediately. And we're down to about 80% of the energy that we could have absorbed if the device was constrained completely so it can't move. And this indicates to me that surging motions are something that are not good. They're not the sort of thing that we want. And we want to design moorings that are going to constrain those surging motions, because what we really want is up to this 80% or even higher. So what can we conclude about this? In general, motions for this type of OWC are undesirable. We don't really want them if we can remove it. Relative to the fixed condition, we can expect about a 40% reduction if we constrain surge, but we let it heave and pitch. And if we let it surge and we let it heave and we let it pitch, we're going to lose about 85%. Now, in a bit of other work, which I'm not going to present too much on here today, we looked at designing a catenary mooring system to see how that would affect the motions. And what we found with the catenary is that it would enable quite a lot of motions, which basically eliminates it from further research for what we're doing, because we already know that surge, heave and pitch is not good, and we're going to get those kind of motions with our catenary. And what we're looking for are moorings that are more likely to, moorings that restrain motion are more likely to increase the hydrodynamic performance. So at the moment, I'm currently testing in the model test basin a vertical taut mooring system, kind of like a tension leg platform. And I know it's difficult to see, but essentially we've got a mooring line that runs straight out of the bottom of each of the cylinders to the floor, and the device is taut, okay? And then a second mooring where we have another taut mooring, but the moorings in this case run at 45 degrees from the fair leads on the columns down to the seafloor. And then thirdly, we'll test a hybrid catenary / taut mooring, which will likely be a taut mooring at that 45-degree angle with a very heavy catenary down the bottom here. And this may allow a little bit of compliance in the system. So that's the operational side of how motion affects the performance. But what about survivability? What about extreme waves? And what I've got here is a series of photos which show a wave that was generated with the new wave theory. And this wave basically sets up and then breaks and slams into the front of the device. These photos were taken when the device was softly moored to observe how it moves. And just a couple of days ago, I made a very similar wave with a tension leg platform. Hang on a second. And then slammed it into the front of the device. Now, if we look at that a little bit slower, sorry, this is not the right one. Let's try this one. Rightio. So here comes the wave, and it slams right into the front of the device. So what are the effects on the moorings? Now, as that wave sets up, we can see that it starts to interact with the columns. It starts to concentrate, and then in the sound, you can see there's a pocket of air in the front of the chamber, and then you end up with this large slamming, smashing into the front of the device. Now, on the side of the device here, what we have are pressure sensors that are designed to pick up what the slamming forces are for that wave. That'll be the subject of a little bit later on once we've analysed this information. This was done not very long ago. So what did it do to the moorings? This is what the shape of the wave looks like. It's highly nonlinear. The wave is approximately 300 millimetres, it set up and broke right on the front of the device as it was. And here we can see how the moorings responded. Now, this is not really quite what we want to see. First things first is these flattened bottomed out points that we can see along both of the forward and the aft moorings. This is because the trough of the wave was so large that the device heaved down, and the pre-tension in the moorings, because they're taut, basically went to zero. So they're maxed out. This is the dynamic tension. There's no pressure, there's no tension, and then all of a sudden we have this snapping, snatching motion on the inside of the OWC on the moorings, and we have a very large response at that particular point. Now, if we zoom in and have a look at that region where those boxes are, what we can see is this high frequency, almost like ringing response in the tendons, kind of like a guitar string that's been strung. Now, whether those responses are directly from the wave slam or whether they're a combination of the wave slam and then the fluid dynamics that are happening on the inside of the chamber, it's difficult to tell. Now, when you look at the survivability for the OWC, the orifice is actually closed. Okay, so it's not open like what I explained before. It's closed off and sealed. So we're trying to prevent the motion of the water on the inside of the chamber from affecting those moorings, because if we open up that motion, the mass of the water that moves on the inside of the chamber increases the load on the moorings enormously. Easily, so for memory, we're talking about 8 to 9 kilos of load. I think we were getting about 14 kilos of load in each mooring line just by opening the orifice up. So that survivable condition is really quite important to make sure we can shut these devices down. Otherwise, it's unlikely they're going to survive a wave like that. And that's basically where I'm up to. But before I finish, I'd like to thank Greg and IMarEST for their support through my PhD. It's been very, very grateful for that. And I'd also like to acknowledge the support of my supervisors who have always directed me the right way.
Thank you very much, Eric. A terrific presentation. I look forward to seeing the complete results in the future so that it can direct the way in which these water column generators are actually moored. We have some questions coming in. And there's one here from Gary Bentel. Are you considering hydrodynamic dampening in a combination with catenary moorings?
Yep. So originally, what we tried to do was damp a lot of the motions with the heave plate that's on the outside of it. And the thought is we want to try and understand whether it's how it's going to perform in the free floating condition, because we know that if we have taut moorings, the loads in those moorings in those large waves is going to be very high. And so we did like the idea of using catenaries, but because you lose so much power, it becomes difficult to design something that's actually going to be economically viable. Now, I do think there is merit in trying to dampen the motions with a plate on the catenaries, but it's outside of the scope of what I'm doing at the moment.
Thanks, Eric. There's a question from Cameron Matters. What does the surge motion look like?
The surge motion? Yep. The surge motion looks like most other devices when it surges. When the moorings are coupled on the at the center of gravity, the device just surges backwards and forwards quite nicely. There doesn't seem to be too much interaction between the heave and the pitch. Now, in saying that, the Decay test that I did today in surge showed really clear coupling between surge and pitch. So the way that the moorings are configured will absolutely create coupling for this particular device. And in fact, if you then start looking at sway, if you do a sway decay test, what you're going to find is you get coupling between sway, roll, and also yaw because of the heave plates and the asymmetry.
Thanks, Eric. Martin Reynoldson, who is a man well known in the naval architecture world, particularly down at AMC, has asked that how were the initial design of the device, its dimensions, etc., decided, and would it be possible to change these such that having motion is good?
Yep. Okay. So the original design and the geometry of the device was largely governed by the incoming wave field. So what you're trying to do is you pick your location and then you design as much as you possibly can to get around this. Now, to make it perform the best that you can. Now, when it comes to the motion of the device, I did quite a lot of CFD and engaged the different degrees of freedom, heave, pitch, surge, and whatever else I could to see how it interacted. And what I found is if the structural motions are too close to the heaving motions, the device will move and the water inside the chamber will move at the same rate. And the problem with this is there's no differential pressure inside the chamber, which means that you don't absorb any energy. Now, it is possible to design one of these chambers so that you can make them heave largely and produce power at the same time, but I don't think it's something that's going to work for this specific type. It's definitely something you can do for the Sparboy OWCs, and yeah, I don't know. I think there's going to be lots of different ways that this can be done.
Thanks, Eric. Another well-known person in naval architecture circles, a man called Phil Helmore, has asked, could you comment on the performance of the King Island installations?
Yeah, I'm really interested to see how this device goes. I think it's going to perform quite well. It's really difficult to know what the specifics are going to look like. I actually quite like the way that they've used the unidirectional turbine. I think it simplifies the whole power takeoff system, and yeah, I think that time will show us, and I hope that it does perform properly, because it'll be encouraging for other people that are trying to develop this technology. We kind of need to have more full scale devices out there so that we can learn from and get a bit more confidence in this industry.
Thank you. I suppose that ties into this question from Howard Tantail about the commercialisation of the work. Where do you see this heading?
Yeah, okay. So at the moment, it's the design of the device is largely around understanding the motion and the moorings. So I think that there's going to be a lot of really good take-home points about what the actual design should be, but I do think it will need a bit of a revision because, on one hand, the device was designed to increase the natural periods of the device away from the wave field, but it looks more likely that it's going to be a tension-leg platform style of device, and that means that the geometry of the device is going to be readjusted somewhat. When it comes to commercialisation, I don't know. I'd like to see this sort of technology being employed, but there's still quite a lot of questions that we need to research a bit further. Thanks,
Eric. Mitch McMahon has asked a question around the power takeoff. Probably more particularly about the survivability of your power cable or the umbilical, and what effect that might have on the allowable motions and its survivability.
Yeah. So I think the electrical connection is probably one of the highest risk parts of these devices. Well and truly, because it's submerged, there is going to be motions around, and there's going to be a lot of marine growth as well. So I think that the power line is going to need to be compliant. It's going to need to have a larger range of motion than the actual device has itself, because this way you're going to reduce the stresses that are actually on it. But it does need to be thought out very carefully, and it needs to be deployed carefully, because damaging that power cable is your blood supply. If you can't send the energy back to wherever you need to send it, there's no real point having the device out there.
So you believe that the umbilical won't provide sufficient dampening of itself to affect the generating power of the oscillating column?
No, I don't think it will have a significant impact. Not compared to the tendons that are keeping the thing relatively still. So I mean, it may have some impact, but I wouldn't imagine it to be a huge effect.
Okay, thanks, Eric.
Yep.
I have a question here, and sadly I can't pronounce this gentleman's or person's name. They've asked whether you could restrict a particular kind of motion in real time in order to increase energy efficiency. And I think what they're trying to get at there is that could you actually have a mooring system that is reactive to the type of motions that are being felt, so that it will then react to make sure that we have the maximum amount of energy absorption?
Yeah, that is something that you absolutely can do, and is currently being developed in Europe, definitely. There's a lot of reactive moorings that are designed to change the phase of the motions, exactly like you're saying. So what you're trying to do is when the device is heaving upwards, or when the water inside the device is heaving upwards, you actually want the device moving downwards, because it will increase the pressure and the flow rate inside the chamber. So you can do it. It's highly complicated. Lots of companies are trying their best to make it work, and it's the irregular nature of those waves which makes the control system very difficult to work with. Now, I'm not a huge fan of this idea at this stage, because I think it's adding a lot of complexity to a very complex system, and the cost of maintaining these this kind of a system, especially in a subsea environment, is very high. And I think that we're better off trying to move towards very passive systems that are inherently simple, and let's optimize those and make them work. And then we can add, more complex systems once we've got a fundamental that's going properly.
Thanks, Eric. Yes, I think there's a lot to be said for the KISS approach. John Clemesha has asked, can you describe applications envisaged for this technology? In other words, for example, putting in semi-submersible rig legs, actually turning those into generating devices.
Yeah, look, I reckon there's lots of applications that could be used with this kind of technology. I mean, I think of like anywhere that we use energy out there in the ocean is a potential opportunity. I mean, you think about all those ports and harbours and all the channel lights that we have. That could all be small oscillating water columns. Really quite easy to do. I think that anywhere where there's an offshore platform, I don't think you can rely completely on the wave energy, because there are times when there's not enough energy available, or sometimes the conditions are too large, or sometimes your energy demand is too high. But there's always the opportunity to supplement the power that you use, which will mean, for the offshore aquaculture, a lot less risk, because at the moment they're trying to, use diesel electric generators, and they're having to cut a lot of diesel out there to make these things work. And yes, it is reliable, but what happens when you spill that diesel? And I mean, I know people are doing the best they can to avoid that from happening, but inevitably accidents happen. So yeah, I think we should be looking at how we can integrate it as much as possible.